another lesson. Now, in this lesson, discuss linear magnification for lens. So, in the topic linear magnification, let us define what is linear magnification produced by a lens and derive the expression for magnification produced by a concave or your convex lenses. So your linear magnification is defined as the linear magnification produced by the lens is defined as the ratio of the size of the image formed to the size of the object. So if small m denotes your linear magnification, then according to the definition, your small m can be written as the size of image to the size of object. Equals to size of image is denoted by h2, then size of object is denoted by h1. So your linear magnification can be written as small m equals to h2 upon h1, right? So this is your formula for linear magnification. Now let us derive this linear magnification formula for your convex lens. So I'll write down first, we'll derive it for convex lens. Now consider a convex lens. Suppose this is your convex lens. Now consider a line which passes through the center. This line is your principal axis. Fine. Okay. So if this is your principal axis, then for your first surface, this one, let this point be your focus and this point be the center of curvature. Similarly, for your second surface, consider this point as focus and this point as your center of curvature. Fine. Let me draw a little bit bigger convex lens, okay? Fine. Now consider an object AB placed between the focus and the center of curvature. Now the ray which starts from point A. Okay, let us consider a first ray which starts from point A. This ray moves parallel to the principal axis. After passing through the lens, it undergoes refraction. So after refraction, it passes through the focus. Now let us consider your another ray This ray also starts from the point A, but it passes through the optical center. Optical center means the center of the lens, this point, right? So another ray passes through the optical center and it passes undeviated, fine. So can you see the two rays intersect at this point, fine. And one more important point, whenever we draw any ray diagram, okay, always also draw the arrows in which the light moves. Suppose for this first incident ray, the light it moves in this direction, fine. After refraction, it moves in this direction. Similarly, for your second ray, before refraction, it is moving towards the point O. After refraction, it is moving here. Okay, so never forget to draw the arrows. Okay, this arrows determines in which direction the light flows. Fine. Now consider the intersection. At this point of intersection, the two refracted rays intersect. If the two refracted rays intersect, then an image will be formed at this point. Okay, so this is your image and it is formed in the downward direction. Fine. So this image is A dash and B dash. Fine. Thus your object AB forms the image A dash B dash. Fine. Now consider the triangle AOB and consider the triangle A dash O B dash. Fine. These two triangles, triangle A dash O B dash. Now these two triangles are similar. I can show them similar. Fine. Let us consider this first angle. Okay. These two angles will be equal by the property of vertically opposite angles. And this angle will be equal to 90 degree and this angle also equals to 90 degree. So both of these angles are equal. So by the property of AAA, that means angle and angle, I can show that these two triangles, your triangle A dash OB dash and triangle AOB are similar. Fine. Now if these two triangles are similar, then the corresponding third side, or sorry, the corresponding third angle, angle A. Okay, let me draw here. This green angle should be equal to this angle. Fine. So these two triangles, your triangle AOB and triangle A dash OB dash are similar. So let me write down here. Triangle AOB is similar to triangle A dash OB dash. Fine. Now, if these two triangles are similar, then the ratio of the corresponding sides should also be similar. So let us consider this angle, the vertically opposite angle. Okay, this angle. Fine. So I've written triangle AOB is similar to triangle A dash OB dash. So consider these two equal angles. Fine, consider your angle AOB. Now the side opposite to this angle is AB. Fine, and consider the other equal angle, your angle A dash O B dash. Fine, this angle, and the side opposite to this angle is your A dash B dash. Fine, so I can write down the ratio of the equal sides A dash by B dash divided by A B should be equal to the ratio of the other corresponding side. So consider this angle, your angle OBC. Fine. The angle opposite to this one is this one, angle O dash A B dash. Now the side opposite to this angle, this one, your side OB dash. Fine. Similarly, the side opposite to this angle OB. So this ratio should be equal to this OB dash by OB. By the property of similarity of triangles, I can write the ratio of the corresponding, or I'll say the ratio of the equal sides, or the ratio of the sides corresponding to equal angles should be equal. So in this case also, this is the ratio of the sides corresponding to equal angle. This is also the ratio of the side corresponding to equal angle, and they both are equal to each other. Fine. Now, by applying the new Cartesian sign convention, I can write down applying the new Cartesian sign convention. So consider your side A dash B dash, or I'll say B dash A dash. Okay, this represents the height of the image. So this is H2. Similarly, AB, fine. This represents your object height. So this is H1, fine. So your according to this sign convention, your image height A dash B dash should be negative H2, since we are measuring it in the downward direction perpendicular to the principal axis. Fine. Now consider your object height AB. Now, since your object height is measured in the upward direction and perpendicular to the principal axis, in that case, your object height H1 will be positive. Now, consider your object distance. This is your object distance OB, and your object distance is represented by small u. Fine. And your image distance is OB dash. This image distance is represented by small letter v. Fine. Okay, so let me just move this little bit upwards. Fine. So your object distance O to B. This object distance will be positive or negative. It will be negative since it is measured in the opposite direction. Fine. See, it is measured in this direction, but the light flows from left to right. Fine. So if it's in opposite direction, I will give a negative sign here. So your object distance is represented by U. So your object OB, or sorry, your object distance OB equals to minus U. Similarly, your image distance OB dash will be positive since it is measured in the direction of the incident line from left to right. In that case, I will write down plus V. Fine. So I will substitute these values here. Fine. So instead of AB dash, I can write minus H2 by AB equals to plus H1 equals to OB dash is the image distance plus V, and OB is your object distance minus U. Fine. Now this minus and this minus can get cancelled. Fine. So let me cancel this one. So H2 by H1. Can you see? Now H2 by H1 is the linear magnification for your lens. Therefore, for convex lens, your linear magnification M equals to H2 upon H1, which in turn equals to V by U. Fine. So this is for your convex lens. This is the formula of linear magnification for your convex lens. Now similarly, you can consider for your concave lens. Fine. So let us write down for your concave lens. Okay, let me draw your concave lens. This is your concave lens. Now consider a line which passes through the center, your principal axis. Okay. Fine, this is your principal axis. Now, fine. Now for your first refracting surface, consider this point as your focus. Now consider an object AB. This is your object AB. Fine. Now for your object AB, let us consider a light which starts to move from the point A, and it moves parallel to your principal axis. Fine. Now this ray, after refraction, it diverges. Okay. So it appears to diverge from this point F. Now consider your another ray which starts from the point A and it passes through the optical center O of the lens. Fine. Now this ray passes undeviated. Fine. Now can you see this point of intersection? Now at this point of intersection, an image will be formed. Fine. Let us name this image as A dash and B dash. So your object AB forms a virtual image A dash and B dash. Right, let me just make this little bit bigger. Now, in this figure, consider your triangle AOB. Fine. And similarly, consider your triangle A dash O B dash. Fine. Let me just use a different color for this one. Let me represent by red. Fine. Fine. Now, your triangle AOB and your triangle A dash O B dash will be similar. So I'll write down here triangle AOB is similar to triangle A dash O B dash. Now again, by using the property of similar triangles, I can write the ratio of the corresponding sides to be equal. Fine. So I can write A dash by B dash, A dash by A dash B dash upon AB should be equal to OB dash OB dash upon OB, OB dash upon OB. Fine. Now again we can, from the sign convention, so I'll write down here, applying the sign convention, Fine. So according to sign convention, if A dash B dash, this represents your image height. Fine. So let us denote this one by H2, and if AB represents your object height, which is denoted by H1. Fine. So according to your sign convention, the image height A dash by B dash equals to H2, and H2 will be positive since it is measured in the upward direction and it is perpendicular to the principal axis. Similarly, your object height AB is also measured in upward direction and it is perpendicular to the principal axis. So this one will also be positive. So I can write AB equals to H1. Fine. Now consider your object distance. Your object distance will be OB. Fine. Your object distance is represented by small u. This object AB forms an image A dash B dash, which is at a distance OB dash from the center O. So this is your image distance represented by small v. Fine. Now look at your object distance. Your object distance is measured in the opposite direction from right to left. Fine. And the incident light flows from left to right. That means your object distance is measured in the opposite direction. In that case, your object distance will be positive. So I can write OB as OB as minus U. Fine. Similarly, your image distance OB dash, this is also measured from right to left, which is opposite to the direction of the incident light, which is from left to right. So since your image distance is measured in the opposite direction, so OB dash, which is your image distance, should be negative, and it is represented by small v. So OB dash equals to minus v. Fine. Now I can substitute these values here. So A dash B dash is the image height, which is represented by H2. AB is your object height, which is represented by H1, should be equal to OB dash. OB dash is the image distance, which is represented by minus V, divided by OB. OB is your object distance, which is represented by minus U. Now this minus and this minus can get cancelled. So let me rub them. Fine. So it will be simply V by U. And we know the magnification or your linear magnification can be written as H2 upon H1, which in turn equals to V by U. Fine. So this is your linear magnification formula for concave lens. Fine. Okay. So to sum up, we have defined about your linear magnification. The linear magnification is the ratio of the size of the image to the size of the object, which is h2 upon h1. Fine. And for your convex lens, your linear magnification, which is represented by small m, can also be written as m equals to h2 upon h1 divided by v upon u. Similarly, for your concave lens, your linear magnification can be written as h2 upon h1 equals to v upon u. Fine. So, and if you have any confusion or doubt, please don't hesitate to ask. I will re-explain it to you again. Fine. So, in our next class, we will solve a numerical using this linear magnification formula and your thin lens formula. Fine. So that's it. Thank you.